let's get started. This week we're going to talk about borrow checker and ownership, which is like the defining feature of Rust. Oh, so some announcements. Let me just share these slides on the Discord real quick because I remember
Rust is language of the week.
I remember people wanted the slides before the meetings, but I forgot.
You can tell there were a lot of people in the meeting.
Yes.
The recording won't show it, but we have like 40 people in the room right now.
Yeah. We have a lot of people. They're just very silent because they're eating our snacks.
That's true.
That streamer mode is enabled.
Okay, slideshow again. Okay, so some announcements. Number one, shout out to Matt Wang. If you're watching this video, Matt, we appreciate you for highlighting Rust as language of the week in your CS 131 discussion today. Also, shout out for Daniel for sharing the article When Rust Hurts. It's always interesting to see like the pitfalls of language because every language has trade-offs and Rust isn't perfect. So this is an interesting exploration of when Rust gets in your way. We can actually apply today's content to actually understand one of the article's arguments if you haven't read it yet. We'll go through it at the end. And then there's new Discord channels. I don't know if you guys have seen, but there's the toy product channel and the core utils channel. The toy product channel is for like anything regarding your toy products. So if you have questions or like if you're stuck on something, just send your questions there, and like when we're free, we'll take time to help you. Or if you're like really proud of some progress, like you hit a milestone, you finally got this thing working after like 10 hours. You can post it in there, and we'll like we'll definitely highlight your milestones. And then also the core utils channel. This channel is specifically for the open source projects. I haven't posted much in there yet, just like some basic info about the core utils repository and stuff. But if you have any questions about the open source projects, please put it in there so I can address them. And finally, I finally emailed Silvestri about contributing to core utils. So Silvestri is like the lead contributor to the core utils, the Rust rewrite of core utils. And he gave me some pointers on running tests on the repository. So if you guys are interested, I can show you guys that at the end. But we should still be focusing on our toy products, of course. So that's it for announcements. Okay, so let's. Have you guys heard of ownership before? Like Paul, Alex, how familiar are you with the term ownership? Like, how many times have you heard before? Oh, I'm also only calling them Paul and Alex right now because even though there's 40 other people in the room,
They're all just eating snacks.
yeah, they're just way too busy eating snacks. And Paul and Alex are the only two people kind enough not to eat the snacks and answer my questions. All right. Okay, so let's start with ownership from a C++ perspective, right? So there's like some basic things that you learn when you learn C++ in like 31, 32. All variables are associated with a memory address. A variable's value is like the bytes stored at its address. So maybe let's take a look at this sample C++ code. Like, what would be the behavior in the memory when these lines of code execute? Ideas? Alex, what happens when we say scaredy cat equals 1 ampersand shared? What does that do?
It makes scaredy cat equals 1 and ampersand.
Yeah, it like creates an object, right?
Is that a struct? Because it doesn't say struct cat.
It's an initializer with construction.
Oh my god.
Let's not get
I'm
into that, but
consistent
it makes an
But yes,
object,
okay,
right?
that
So
makes sense, yeah.
scaredy cat is some objects. I mean, I can show it. Okay, let me just show you the source code for this cat is a struct that contains an integer and an integer pointer. So
I hate that C++ allowed this dumb initialization.
yeah, it's like it really complicates the initialization of objects.
No.
But okay, so well, scaredy cat is an object. What would this do? What would this line do? Cat mins equals scaredy cat.
It makes a copy.
It makes a copy of. So does mittens? So like, what's the relationship between mittens and scaredy cat? Like, do they have the same address?
No.
Is mittens a copy? I forgot how C++ does this.
Yeah, in fact, mittens is a copy. So mittens would be a separate object, right? So it would have like a separate address from
Yeah.
scaredy cats, but they would have the same contents, aka the same value, right? Because the values is the byte stored as its address. So it would have the same contents, it would have the same value, quote unquote. But what can be a problem with copying scaredy cats and mittens in this definition of the object? I guess.
I have an idea.
Yes,
The
Jason?
pointer inside still points to the same address.
Yeah.
Yeah, so scaredy cat is an object, mins is an object, but they both have a pointer to something, and that pointer is pointing to the same thing. That's gonna be a problem later. What about this guy? Cat angry cat, cat ampersand angry cat equals scaredy cat. What does that do?
C++ next is
It
weird.
makes a reference.
Oh, that is a reference. Okay. Is that a pointer or a reference? Because there's like a difference, but it's like I don't know what the difference is.
You don't actually have to explicitly dereference references.
Oh, that's weird. Okay.
Yeah. In my opinion, pointers and references are kind of just like semantic sugar for cost pointers.
Yeah.
Um,
Oh, okay.
but technically, every variable has a unique memory address. So technically, angry cat has its own memory address, right? Like technically, angry cat has its own memory address. And what's stored at angry cat's memory address? What's stored is actually a pointer to scaredy cat. So technically, angry cat and scaredy cat are different types, because angry cat's value is a pointer and scaredy cat's value is this struct over here. But the thing is that whenever you're using it, C++ would implicitly dereference this pointer and then do the operation on the object represented by scaredy cat. So now we have objects, copies, and references. Anyone remember move constructors from CS32?
Yes.
Wait, they talk about moves actually?
Yeah, I believe so.
That is amazing.
Paul, do you remember move constructors?
Yeah, I remember there's like a rule of 3 you get to follow, but it was like really obscure. Something about the copy and swap idiom.
Yeah. So, what's the purpose of move constructors?
So you can move into a different variable.
But like, like, yeah, that's like
Yeah.
using the verb move, but like, what is its purpose? Like, why
I think
would
it's-
we want to move?
I think it's to avoid a copy. I'm not quite sure.
Avoiding copy? So, yeah, it's for efficiency reasons. And indeed, we can avoid a copy. Moving allows us to take efficiency shortcuts by stealing data from temporary objects instead of copying. So yeah, perfect. You got it. It enables us to steal data. But the catch here is stealing, right? Because instead of copying, you can't really just have another object. Like, you have to take its stuff somehow. And the only other way to do it instead of copying is by stealing it. And we cannot. The restriction to moving is that we cannot move values that are bound to a variable, because accessing those variables later will lead to nasty results. So suppose I just took your property, right? If I just like took your property, then
Yeah.
like if I broke into your house and like stole your TV, and then you go back home later, you try to access your property again, like it's not there anymore. Right? It's
Wow,
like that's a
incredible.
problem. So you can't move values that are bound to a variable, but what you can do is move values that are temporary. So let's say, okay, this is a very unethical comparison. Okay, I probably just shouldn't say it. Anyways, so imagine like you're a bully or something. Like you're always gonna bully the kid who's like alone, right? You're not gonna bully the kid who has like 10 friends because they're all gonna like
I'm gonna beat you up.
So you have to steal only from values that are temporary, not values that are bound to a name.
Wait, what is actually a temporary variable in this case?
Oh, a variable is anything that has a name.
Oh, sorry, temporary object. What is it?
A temporary object. Well, let's see. In this example, we have a cat. I just put a struct there because I don't want to make stuff public.
Oh, wow.
So here we have a regular initializer where you pass in an int pointer and it initializes the value. Very standard stuff. And then here you have a move constructor. And here you have cat. This constructor takes in a temporary cat. This temporary cat is denoted by the double ampersand. Let's not get into too much into the syntax here, but it takes in a temporary object, and it literally just says my C is equal to temp C, and temp C is now null pointer. So we have effectively stolen the data from temp. And if you look at the usage over here, let's say scaredy cat is a variable. Scaredy cat is a cat that's bound to a name. So what we cannot do is we cannot initialize mittens by moving scaredy cat into it, because then we would be stealing data from something that has a name. Something we can do is we can initialize this cat, Grumpers, with a temporary cat. This is a cat that has been initialized, but we haven't bound it to a name yet. So it's kind of just like floating there, and we can steal its stuff and move it into Grumpers, right?
Yeah.
The idea is that, I guess, if you take anything away from all this is like, can't steal stuff from named variables, and when you're stealing stuff, you also have to set the other guy to null pointer, because if the object that you're stealing from is still holding onto your data, then when that object deletes itself, then it'll also delete your data. So you also have to make sure that the object that you're stealing from is no longer holding onto your data. Okay, so that was a little complicated. Okay, let's go. I have this aside over here. There's a lot of nuance with different properties of values, as we said before. There's we can move values, we can copy values, we can reference values, right? C++ has 5 value categories: L values, 3L values, X values, R values, and PR values. That's like so complicated. That's like way more complicated than what Rust has, in my opinion. And this excellent Stack Overflow thread discusses their differences, and I think it's really interesting. It's a really interesting thread that really goes into a lot of the nuances here. And this picture over here is actually a diagram drawn by Strostrup, the inventor of C++, on the properties of values, right? So according to Strostrup, there's like 2 orthogonal properties of values. Number 1 is whether it has identity, and that's represented by these i's here. And then number 2 is whether you can move it, which is represented by these m's here. So any value either has identity. If it has identity, it's bound to a name. Like over here, we saw that scaredy cat has identity because it has a name. You can like say scaredy cat, or you can say scaredycat.c, and you can refer to it. Another property of values is whether you can move from it, right? So this cat over here does not have a name, it's just floating there, but it can be moved from. So that's another property of values. And Strostrup drew this diagram to show that literally all values, like all these stuff, L values, GL values, X values, all this stuff can be thought of as just combinations of whether it has identity or whether it can be moved from. And I think this is really beautiful. This is like the kind of thing that makes me really excited about programming languages, is because you took this idea of like references, pointers, all that complexity, and you just condensed it into two properties, movability and identity, and drew this very simple diagram. Although like without context, like I really encourage you to read this Stack Overflow thread. Without context, it kind of doesn't make sense, but it's really simple, right? This encapsulates all of the different properties of C++ values, and I think it's really beautiful. The conciseness of this depiction, of this expression, everything that we've assumed about memory and all their complexity is nothing more than this.
So I like the C++
I mean, it's not about C++, right? It's about like languages. It's about like the ideas. Okay.
Wait, what is identity, by the way? Is that similar to our study of aliasing?
Identity is what, well, according to Strostrup, it's like whether a value has a name or not. Like, security cat over here has a name. Yeah. But like the idea of Rust on the other hand goes through another approach, right? Like Rust doesn't do this stuff. It has its own borrow checker rules. There's 3 borrow checker rules, as you'll see later. But it's still very simple, concise, and elegant. Even though like this is Strostrup's idea, I think it's cool. Rust has their own set of axioms that govern memory safety, which is also very cool. So it's like all programming languages, their ultimate goal is to take all those complex ideas about programming. Like you could be programming in assembly, right?
Yeah.
Like moving, like move L and like jump and calls and whatever. But all programming languages, their goal is to take those complexity and present it in such a nice and elegant fashion that it's natural and it's it's beautiful. And here's a quote from Alexander Pope: "True wit is nature to advantage dressed, well oft with thought, but never so well expressed." And I really resonate with this quote because it's like what I said about Strostrup's like expression here, right? Like it's so well expressed. Rust idea of ownership is so well expressed. It takes all of that complexity and just expresses it so naturally that we're like, wow, why didn't we think of this before, right? Anyways, okay, that's enough showing for me. Ownership from a C++ perspective. Now I'll end the show about C++ and just talk about some big ideas. Some operations we want to support on objects. Number 1, copying. Sometimes we just need a copy, right? Like sometimes you just want another copy of the thing that you have right now. But the pitfalls, right, are shallow versus deep copies. When your structure contains a pointer to some other data, and then you just copy that structure, that's a shallow copy. Memory usage, right? If you copy too many objects, there's memory usage, and there might be memory leaks. Another thing we want to do on objects is referencing. We want to access an object. We want to be able to read its data, but we don't want to copy it. So we use pointers for that, right? References, pointers, pretty much the same thing. But now we have other pitfalls. We have invalid references, where maybe you deleted an object, but you still have a reference to it somewhere else, and you try to access that reference. Segmentation fault. Aliasing, two variables are referencing the same object. One changes, the other one gets surprised. Race conditions, right? When you have references in different threads, like try to access the same object at the same time. Race conditions. Moving, we want to steal data from temporary objects. The pitfalls here are we better make sure that the object we're stealing from is actually temporary, because if you're stealing from something that has a name, try to refer to it later, it's an invalid reference yet again. So these are the operations that we want to support on objects. And this is not just C++, right? Like Rust has these ideas too. So they're just presented in a different way. Okay, so I'll like talk about the basic Rust ownership here, and then Jason will take over. So the 3 basics rules, each value in Rust has an owner. There can only be one owner at a time, and when the owner goes out of scope, the value will be dropped. If you have read the Rust book before, this is very similar. In fact, I copied and pasted this from the Rust book. Okay, so this is very concise, right? Like, as I was saying before, it's just a very concise expression. Okay, so the divergence from C++ here is that this will not compile Rust. Let string 1 equals string from hello. So this creates a new object, just like we did with cats, right? We created a new cat. That's nothing surprising. But if we let st equals s1, then we try to print out s1, it will actually fail. And here's a compiler error. Anyone find anything suspicious about this, or like interesting about the compiler error? Any like connections to the ideas that we talked about, like the big ideas of either copying, moving, referencing? Anything in here rings a bell?
Yeah, I find it curious how there's no colors.
That's also because I screenshotted this from the Rust book.
I was gonna say the file name is really funny. It's just file/project/ownership.
Yes, I screenshotted this. This is not run on my own machine, unfortunately. I was too lazy. But like we see like the terms like move here, right? Like move, borrow. Actually, we haven't talked about borrow yet. But moved. Okay, moved. Is that ringing a bell here? Move occurred is because S1 has type string. Now value moved here. Okay, why would it be moving there? Let's think about that. So let's apply Rust ownership rules. Which rule applies? Let's take a look at the rules. Right. So 3 basic rules. Each value in Rust has an owner. There can only be one owner at a time, and when the owner goes out of scope, the value will be dropped. So which rule applies? Which rule is preventing us from compiling this code? Alex?
Because Rust assignment doesn't move, and then you can't use the original one after you move it.
Yeah, so which rule do you think would, which of these 3 rules do you think apply?
There can only be one owner at a time.
Yeah, perfect. There can only be one owner at a time. Okay. The compiler outputs tells us that the value of S1 was moved into S2, which I kind of very obviously hinted at here. Value moved here. S1 was moved into S2, and okay, let me just open these bullet points. So remember in C++, when we did mittens equals scaredycat, it copied scaredycat into mittens. So C++ copies by default. And the reason why it does that, I don't know if there's a reason why, but like the nature of it is that C++ wants to make sure that a value's identity is always respected. A name will always be valid, right? If you do mittens equals scaredycat and you try to access scaredycat later, it will be a valid object. And in that way, like you'll never get any surprises when you're accessing names. But Rust moves by default. Rust wants to make sure that ownership rules are followed in order to eliminate memory bugs. So it always follows these ownership rules, even though, right? It always follows these ownership rules, even though the result might be something that you are surprised by. Your variables don't work anymore, right? You can't access your variables anymore. But that's because you have to keep these in mind. So with a move, right? Again, S2 is stealing S1's data. So now when you access S1, S1's data was stolen. So it's kind of like you went back to your home and noticed that your TV was missing and you have a broken window. So obviously this will be a compiler error. Okay, so So that was like a simple application of Rust ownership rules. Let's hand it over to Jason.
Okay, so we're just gonna quickly go over some like common errors that would work in C++ normally but don't work in Rust because of ownership rules. So also, first of all, actually, wasn't there a slide before this on the? Oh right, I forgot. This was just an introduction slide. So, you know, you might have seen like if you have a vector and you try to like call it twice in a function, it won't work because the first call will move it, right? In order to avoid a copy, because you can just, you know, copy the data pointer without having to copy every element, which is very efficient, which is why it's moving by default, but then you can't use it again. And then also if you like have an outstanding reference to one value in the vector, you won't be able to push anything into it, and you should not be able to push anything into it because this is invalid in terms, because, right, pushing to a vector may reallocate it, which would, you know, change all of the references and invalidate everything. So C++ would let you do this, but it's wrong. And then this is just reiterating what ownership is and refreshing the slide because I moved the image down. So a quick like addition, like what can be the owner of a value? So one example of like an owner is just a local variable, right? So the local variable v owns the value of this vector. And once it, like the scope exits, then the vector will be dropped. Another common example of like an owner would be a struct. Like here, the foo struct holds this value, like this vector, and it owns the vector. So once the struct is dropped, then the value will be dropped. And in this case, since the struct is owned by a local variable, it's effectively the same because once you exit the scope, the struct will be dropped, which will cause the vector to be dropped. Oh yeah, also drop is like the equivalent of like free or delete in C++. So again, moving is just how Rust enforces ownership. So like passing values as function parameters or doing assignment expressions will move the value. So it basically changes the owner, and it helps with optimizations. So normally in C++, if you like call a function with a vector, it will copy like every single value of the vector into a new one in order to like ensure validity. That way, if your function like mutates the vector, then you know it won't be mutated in the caller. And that's why they tell you to like take things by const reference impossible and everything. But in Rust, like doing this will just move the vector, which means it can just copy the data pointer since it no longer has to ensure that the original vector is valid, since you can't use it after the function call anyway. And then the exception to moving is the copy trait. So anything that implements the copy trait, instead of being moved, will be copied. So down here you can see if v is a number, which does implement copy, then you can use it however many times you want. Something to note, all immutable references are copied. Since references are just like pointers basically, they can be copied. You don't need to like explicitly clone them. In fact, I'm pretty sure trying to call .clone will invoke deref coercion and clone the actual like thing being pointed to as opposed to the reference itself. Note that immutable references are not copied because you can't have two mutable references to the same thing. So it would be pretty bad if mutable references were copied. For like a comprehensive list of things that have copy, or well not comprehensive, but like a long list, numbers, tuples of things that are copied are also copies. Like a tuple of like I32 and U32, since both of them are copied, it will also be copied. Any array of something that is copied will also be copied. I think there used to be a dumb thing where they like manually implemented copy for like arrays of length 0 and arrays of length 1 and arrays of length 2 and so on up to 32. But that was because they didn't have const generics. I think since they have const generics now, all arrays implement copy. And then also, something to note about copy is that it is a simple bitwise copy. Like, it just literally copies the exact memory layout. And so, this means that, like, you know, things with custom clone behavior cannot be copy because, you know, copy will not invoke the custom behavior. And it also means that anything that is copy cannot have a custom drop implementation, because you could have like accidentally copy it like 5 times and then drop the same thing 5 times, which would be like a quintuple free, which is really, really bad.
Also, they're still not done with it yet. the arbitrary length constant arrays.
Are you kidding me? It's been so long since
I
we
know,
stabilized
it's been
const.
like 4 years. The issue was open on 2019.
So cringe. Quitting Rustations right now.
Quitting.
And then now we're gonna go over the borrow checker, which is like the one thing that makes Rust Rust, in that references to values are tracked at compile time and are like basically part of the type system. So the compile time borrow checker will basically keep track of how many references there are to any value at any given time. And you cannot move or drop anything, and drops are like classified as a move in Rust. You cannot move or drop anything that's borrowed. So from that like example before, where we like took a reference to an element in a vector, you can't pass that vector in as a function parameter because that might change the address, which would invalidate the reference. So the borrow checker enforces this, and also, you know, in C++ you can return like a pointer to a local variable and it won't error. That can't happen in Rust. And you can have a mutable reference to a value if and only if there are no other references mutable or immutable to that value. And for motivation of why this is important, you can go back to the vector example from before. Pushing to that vector requires a mutable reference, which would be very bad if you have an immutable reference to a value of it. And also note that in Rust, having a reference to a part of a value, like a struct field, counts as a reference towards that value. So like even if you just borrow one field of a struct, you still can't move the entire struct. There are like disjoint reference checking, but that's like at a function level and it doesn't work between functions.
Wait, that was one of the arguments in the article, right? Like, you're trying to borrow part of the struct and then borrow a disjoint part of the struct, but then it won't let you.
Yeah. Rust recently, like in the past year, added like disjoint borrow checking for closures, which I think is cool, but yeah, the type system like does not encode disjoint borrowing for like across function boundaries, which is maybe annoying, but and then just a couple of borrow checker examples. This is borrowing the vector, you can't move it. This is borrowing the value, you can move it because you're not actually moving it, you're copying it, so it's fine. And there's another example, you already have an immutable reference, you can't have a mutable one to the same thing. Note that like having the copy trait does not affect this at all, right? Like this is copy, but you still can't do this. Like this is just never acceptable. And it's also relevant when you're doing like multi-threaded programming, because, you know, having like 2 mutable references to something is exactly how you get race conditions.
Wow, fearless concurrence.
And then ways to like get around the borrow checker, but in like very heavy quotes, because, you know, you're like still working within the confines of the borrow checker. If you want to like move things twice, clone the like first time you move it, since, you know, like you do actually just need to make a copy if you want to use it twice. So Rust also kind of forces you to be explicit about when you're doing copies like this. Also, when writing multi-threaded code, consider, you know, because a lot of the time you will have to access something from multiple threads. And so this is sort of a simplified example that doesn't use arc. If you have threads that might outlive the lifetime of main, you will need to wrap the mutex in an arc. But a mutex stands for like mutually exclusive, I think. I think that's true.
Yeah.
And basically, it ensures that to access or mutate the value, you need to lock the mutex, which will wait until no other threads are using it, and then it'll let you mutate it. And then while it's locked, you know, no other thread can also look at it, which basically ensures that it is like, you know, only one mutable reference, and will allow you to sort of like use a value across threads and effectively have like multiple mutable references without any of the issues.
What's the star over here on the mutex?
It's a dereference.
Oh, but it wasn't. Was it reference? Because it's let mutex equals.
The lock returns a mutex guard, which is basically like a smart pointer.
Oh, the lock is the thing that's being dereferenced.
Oh.
Yeah.
Oh, okay.
Also, normally in like actual code, you will see like let v or whatever equal mutex dot lock dot unwrap, and then it'll just be like star v or whatever.
Okay. Yeah.
But like this is just one line, so like I don't need to store it to a variable.
Yeah.
And then also a lot of the time, it's the same in C++ where people tell you to take like const references to things. A lot of the time, you don't need to take own values. Like if you are just reading from a vector, just take a slice and just pass it in as a reference, and that will like avoid all of this. And I guess that's the end of the presentation I prepared, but I could talk a bit more about like owned versus borrowed values if you want.
Oh yeah, what's the difference between copy and clone?
So copy is like this trait that marks it as like an implicit, like whenever, like instead of moving it always copies, right?
Yeah.
Whereas clone is just anything that has a .clone method. So it like
so it doesn't do it implicitly. You have to
yeah.
modify it.
And also clone can have like special behavior for cloning. Like copying is always just like a bitwise copy. You
Yeah.
cannot have any special behavior. So like most things implement clone, but very few things implement copy because of that.
That makes sense. Okay.
So if it implements copy, would it necessarily also implement clone?
I think
Yeah.
so, yes.
Okay.
You can like call clone on like copy stuff.
What?
I think
You
call
can-
clone on like copy stuff, so probably.
Yeah, although I think, if I remember correctly, there might have been some like weird quirk where copy actually doesn't imply clone. I forget,
Wow.
but they I hope they fix that. But actually, yeah, I don't know. I hope they fix it. It would be kind of weird if they didn't. Anyway, I guess some things that we can talk about if. Okay, so does everyone here know the difference between like capital S string and lowercase s string, like lowercase s string? We can go over that. So Rust has this sort of like concept of like owned versus borrowed values sometimes. So like an ampersand, or this is like maybe most obvious with like slices. If I just go to like, I don't know. Yeah, we're gonna, first of all, where's the, there we go. We're just gonna change this to,
Dracula? What's your favorite thing?
Sure, we'll do Dracula. So true?
What is ace?
Where, I hate this keyboard so much. Okay. Alright, this is like completely, is there like a font size in config?
I I can just like open up VS Code for you.
Okay, sure. Oh shoot. Let's see. Open recents. Rust demos. If you want to do that. Okay. Is would you rather do this or do this?
Let's just do Rust Playground.
Okay. That's so weird.
Yeah, you just manually zoom in. This is no awkward thing.
Yeah.
Oh, that UI size, let's go.
Let's go. Okay.
Alright. So, I guess let's make a function that just, like, prints out everything in a, like, vector, I guess. So we're gonna, like, print vals t, debug. We're gonna take a reference to a vector. And we're just gonna say, like, right, and this should hypothetically print out everything in a vector. Stupid. Okay, and you can see it like printed out all of the elements over here. But the issue with this is like, what if we want to like, we have some array on the stack, right? Like, vectors are backed by arrays, so hypothetically this should also work, right?
Would it pass the time checker?
But no, it doesn't because we have an array here, and we took in a vector, right? So a vector is sort of like, it's like what you would consider an owned type because, you know, it enforces that it owns the data on the heap. Like, the data has to be here and nowhere else. Whereas if you took in a slice instead, right, just like change the vector to a slice, this is what people would call a borrow type because the data can be anywhere. It can be on the heap in a vector, or it can be on the slice or whatever. And it can be on the stack. And so you can see this example will work for both, and it'll print like 1, 2, 3 twice. This is why people will say you almost never want to take like a reference to an immutable reference to a vector as a parameter, because it is it is almost never correct. The only time you would ever want to take an immutable reference to a vector is if you, for some reason, needed to get the capacity of the vector, which I can't see why you'd ever want. So that's like the sort of like own versus borrow type thing. And the difference between capital S string and lowercase s stir is the exact same thing. So like capital S string is like vec, it enforces that the data is on the heap and own, and like lowercase s stir, just, you know, the data can be anywhere. And so this like comes up, this becomes a very important distinction when you have like a struct, right? You generally don't want to have like slices in your struct because you want your struct to like own its data so the data lives as long as a struct does, right? If your struct had references, you would need to somehow keep the data alive and at a constant memory address external to the struct, which is like generally pretty hard to use.
So it's like having pointers in your structs, right? Like in the previous example, or not in the previous example, like imagine if you had a struct with some pointer to an object, and then you have another struct with some pointers to an object, blah blah blah. Now you have all the problems that come with pointers and references, which aliasing. I mean, I guess you could have aliasing. You know, like use after free or like use after free and stuff like that. How does like if you did have references in a struct though, like would there actually be use after free
is, like,
with the-
Rust enforces that if you have references in your struct, you have to assign a lifetime to your struct. And then it will basically count whenever you construct the struct, it will now count that struct as like borrows on values. And if you drop those values, the borrow checker will complain just as if you had a reference to them and you dropped them.
Oh, okay. We'll talk about lives another day. But yeah.
Or actually, I might be able to demonstrate it now. We just have like, this is Vim key bindings. So like, this is the syntax for a lifetime. It is like the same as a generic syntax, except you put like an apostrophe before the name. And then we're gonna have some like value, and it's going to be a reference of lifetime A to an I32. And you can like sort of use this, right? Like let x equal 5, let foo equal foo val at a. And actually we're gonna derive debug on this just so we can like print it out. And if you print it out, you should see like it does work, right? Like it prints out val 5. And if you say try to like drop x here, so like let's say let foo here and then create a scope. And then get rid of this. Yeah, you can see it still counts as a borrow. It says x does not live long enough, and like the borrowed value is dropped. So that's like, so lifetime issues in Rust are like very, very annoying to deal with. But like this is the type of error that they stop from happening. Funny enough, there's actually still a soundness hole in Rust that allows, like with nested lifetimes in function pointers, you can actually cause a use after free with entirely safe Rust. And this was known since like 2019.
I think that got fixed recently, actually.
Really?
Yeah.
Wait, is that like? I just wonder like, is it like?
Oh, this is
Rust,
so
is Rust
good.
paradigm like theoretically proven to be feasible? Like, yeah, there's like holes here, but like, is it theoretically proven to be like always feasible, like waterproof?
Yeah, because the thing is, right, you cannot have a perfect borrow checker that like denies all invalid code and accepts all valid code,
Really?
because that's equivalent to solving the halting problem.
Really?
Yeah.
Wow.
So, I mean, like you could just think of it like, you know, you have a value and if it gets dropped, then the program halts, and if it doesn't drop, then the program doesn't halt. Or
Yeah, but like type generics are like feasible, right? Like type generics definitely work in like Haskell and like all the
I heard
functional
that
languages.
Rust type system is Turing complete.
it is. I wrote a challenge for DiceCTF that was a Turing complete Rust interpreter that ran like a weird dialect of Lisp.
What the
That's
hell?
funny. Yeah, the type system is apparently Turing complete.
A
So that also
lot
sounds-
of languages have Turing complete type systems.
Yeah, I've heard that's really hard not to be.
What does it
Turing
mean for a
complete.
type system to be Turing complete?
As in, like, you
Basically,
can
yeah.
write programs in the type system.
Yeah, but what? How does that?
That's a great question.
C++ template metaprogramming.
Is that
Okay, but template metaprogramming is like kind of cheap. It's fine.
It's cheese. We're good.
Isn't like template metaprogramming like kind of cancerous?
Yes. I mean, Rust is also pretty toxic when it comes to like actually writing, you know. Okay, who wants to keep learning about lifetimes and who wants to just goof around and write Turing complete Rust code in the
Right.
type system?
How about we like check up on the projects first? Like and then
Sure.
we can do that
Yeah.
Turing complete. Alright, how are you guys' projects going? Any like updates?
Haven't had time to work on this week unfortunately because of midterms. That's planning to keep working on it. So.
What about you, Alex?
My project is not exist.
Oh,
This is tragic.
oh, that's sad.
So
Wait, have you seen the products workshop slides on the Discord?
It's like a line counter, right?
Yeah, we published the full spec for it. It's in the slides channel. This is also for the recording. In the slides channel, there's a link, or there's a Google Slides called Products Workshop, and that has the full specs for toy products. And the idea is that you're gonna try to implement a parallel file line counter, and then once you do that, then we can move on to working on the actual core utils. I mean, like, obviously, like, if you're feeling really confident about your Rust skills, then we can also just jump to core utils, but please attempt that first. Yeah, so I guess that's it for products. The 40 other people in this room have no updates regarding their product status. Okay, let's just end the recording now because I feel like the Turing complete goofiness is not really viable.